All right, hey guys. So let's see, we were on worksheet 1 right here. We already went through and did most of these, so I'm going to do a brief review. But we're going to pick up where we left off, which was worksheet 1, question number 4. All right, so before we get there, let's do a brief review. So if I have a number like 4,732, and let's say I divide that number by 0.0310, and I want to know what that answer is. If I plug it into my calculator, 4732 divided by 0.031, I get an answer of 152,645.16. And before chemistry, that would have been a perfectly fine answer, but now we've realized that if these numbers are measurements, which you'll be working with almost exclusively in chemistry, like grams, meters, etc., then this number has to rely on the amount of sig figs in this number. So we've got to check this number out first. It's got 4 sig figs, and this number has 3 sig figs. Now remember, when we're multiplying or dividing, our answer I can spell, has least number of sig figs. Maybe even I'll put the same number of sig figs as the number with least sig figs in calculation. Okay, so our answer is going to have the same number of sig figs as the answer with the least number of sig figs in the calculation. All right, so this one had 4, this one had 3. Remember, zeros after numbers do count as long as there's a decimal somewhere in that number. So we know that this answer needs to have 3. In order for it to have 3, every time you multiply and divide, it's easiest to put the number into scientific notation first. So let's do that. We know we got to move this decimal between the first and second number here, so we're going to move it 1, 2, 3, 4, 5 times. So that's 1.52. 64516 times 10 to the 5. Now these two numbers are equivalent, and you should be able to go back and forth between them. But now again, our next point is to figure out the number of sig figs. This had 3, that had 4, therefore this should have 3. So I underline the first 3, and I ask if this number next to underline is 5 or greater. If it's 5 or greater, we're going to be looking at rounding, and it sure is. It's a 6, so we're going to round up. So our answer ends up being 1.53 times 10 to the 5. In other words, 153,000. So you could look at it either way. Both of these answers would be acceptable. Okay, so that's multiplying and dividing. But now we have to also look at another rule, and that's when we add or subtract. So when we add or subtract, our answer no longer has to do with sig figs. It's going to have the same precision as our answer with least precision in the calculation. And we'll talk about what I mean by precision here right now. So when we add or subtract, our answer has the same precision as our answer with the least precision in the calculation. So what I mean by that is, how much do we know about that number? So for example, if I have a number like 45,000 versus a number, it's like 45,000 with a decimal in it. In this case, we only know those two numbers. And in this case, we know all of those numbers because this has a decimal and the numbers come out, or the zeros come after the numbers. So in other words, all of these are significant. This we know to the thousands place, and this we know to the ones place. This one is less precise Sorry, my dog always decides to drink water when I'm recording. And this one is more precise. All right, and that's simply because if this is 45,000, we only know the 45,000. We don't know this one, this one, this one. This number, if you remember, is a range between up one and down one of that number. So this is a range between 44,000 and 46,000. But this one is a much tighter, narrower, more precise number. We know the difference between +1 and -1 of the ones place. In other words, this is a range between 44,999 to 45,001. And that's what makes it very special. So if I were to take these two numbers and add them, in fact, let's go ahead and do that. I have 45,000 plus 45,000 dot. If we added them up, we'd have 90,000, right? But now we figure out our number. Our answer, if you remember, when we're adding and subtracting, has the same precision as the answer with the least precision in the calculation. This one had the least precision. In other words, we only knew up to that thousands place. Therefore, we only know up to the thousands place in this 90,000. Well, we can't just go represent this number like this. We have to show that we actually know that zero, because we don't know if the zero is significant or not the way you have it written. And so we'll have to put that in scientific notation. That would be 9.0 times 10 to the 4. And that is the only way, I believe Andrew asked that question, that we can possibly know that it is in scientific notation. So, as if it's in scientific notation. All right, so I hope that helps. Let's do a few more examples here. Another example, let's say we've got 546.2 plus 310, let's say. All right, when we go to add this, I get a 2.658, so you just add them up the way you normally would. And now we look at the precision. This one we know all the way over here to the tenths place. But this one we only know to the tens place. We don't know that zero over here because it's not significant. In other words, this answer right here, we will only know to the tens place. And so we underline up to the tens place, ask if this number next to it's 5 or greater. It is, so we're gonna have to round up. Our answer is actually 860. You could also represent that as 8.6 times 10 to the 2. Let's do another example here. If you have something like with several decimals, and this is a question we kind of did in class already, 416.13. I don't know, I'm drawing a line. I guess I'll put the other number up here. I'm committed now. 301.2, something simple like that. And let's add those up. This is a 3, 3.7, 1, and a 7. So we get 717.33. This number we only know to the tenths place. And this number we know to the hundredths. Which number is the least precise? That would be this one. Remember, going from left to right. The one we know the most about would be have more numbers on the right. So this is the one we know the least about, therefore our answer should be the tenths. We underline up to the tenths. Ask if the number next to it's 5 or greater. It's not, so our answer is 717.3. All right, so hopefully that gives us enough information now to do these. If you haven't already fast forwarded the video and you're doing them, I hope it'd be great. Okay. So we already did these two. Let's move on to this one. So we have 42.16 plus 71.118. And I'm actually going to line them up because I think it's easier to see it that way. And I threw it in my calculator so I didn't make a silly mistake, and I get 113.278, and I can look at it right now and think that's correct. All right, this number we know to the hundredths place, and this number we know to the thousandths. We know the least about the hundredths, and therefore our answer should go to the hundredths. So we underline up to the hundredths place. Ask if the number next to it is a 5 or greater. It is, so we're going to round up. And our final answer should be 113.28. You could also put that in scientific notation as 1.1328 times 10 to the 2. And then we get to this really fun one right here. It's 20,000 minus 14.23. So if we have 20,000 minus 14.23. If we do that calculation, we get an answer of 19,985.77. But keep in mind, this 20,000 is really a range between 10,000 and 30,000. This only has one sig fig. So if we were underlining how much we knew about it, we only know to the 10,000ths place. This one we know all the way to the hundredths place. So again, just remember, in case you missed this is a range between 10,000 to 30,000. If we have no idea what that number is, only the fact that it's somewhere between 10 and 30,000, we can't possibly care if we're going to take away 14.23, this minuscule tiny amount. And so to prove it to you, we'll follow the rules that we already know. This one we know to the 10,000ths place. This one we know to the hundredths. And so we know the least about the 10,000ths, and therefore our answer should be to the 10,000ths place. So we're going to underline up to the 10,000ths right there. Ask if the number next to it is a 5 or greater, and it is. In that case, we're going to have to round up, and that will give us our answer of 20,000. In other words, you could have taken away a lot. You could have taken away hundreds, and it would have still been 20,000 because we only know, again, up to the 10,000ths place, and therefore any reporting answer will have to be up to the 10,000ths place. All right, so hopefully this is kind of making some sense. Real quick, in case it's not, I'm going to do one more that you're going to find in your book a lot. So you guys might not care about this now, but you're going to see it in your basic chem textbook. And that's 100 minus 18. If I have 100, remember that's a range between 0 and 200. We only know up to the hundredths place here. We know up to the ones place here. Ones. I can spell ones. And so when we subtract it, we get an answer of 82, right? But again, we only know up to the hundredths place. So we underline up to the hundredths place, which would be right here. Ask if the number next to it's 5 or greater, and it is. So you have to round up, and our answer ends up being 100. If that didn't make sense, let's do it a different way. And let's say we have 200 minus 18. It makes it a little easier to see. This would give us an answer of 182. This we know to the hundredths place. This number we know to the ones. So we know our answer has to be the hundredths place. You underline the hundredths place, ask if the number next to it is 5 or greater, it is, so you round up, and this will give us an answer of 200. And hopefully this makes a little more sense to use for that one. All right, time to move on. So in part B, now all of a sudden we're combining things, and we have to pay attention when we combine things using PEMDAS rules. So whatever you would do mathematically first, you need to pay attention to the sig figs or the precision in that particular area. So this first part, if you were to do this math problem, you would do multiplication first, right? So we're gonna do 47.26 times 1.2. And I get an answer of 56.712. And just keep in mind, when we did this, we multiplied. Multiply means we're looking at sig figs. So this one had 4. This one had 2. So this answer should technically have 2. I'm not going to do anything with these extra numbers yet. I'm not going to like get rid of them. I'm going to use them in the next calculation, but I'm going to keep in mind that I should only have 2 sig figs here, to which we're going to add 1.1174. So let's go ahead and add that. And I get an answer that is 57.8294. Now this, remember, even though we use these extra numbers because they're important not to round, otherwise you'll be underselling or undermining your answer. It's going to be smaller than it should be. So we're going to pay attention to these numbers here. They are important, but they are not significant. Remember, when we took this number times this number, we only got 2 sig figs, so we really only knew up to the ones place here. This one, we know all the way to the hundredths, thousands, tenths, hundredths, thousandths, 10,000ths of a place. So we know this number is quite precise. So when we add, remember, we're going to look at precision. Here we know up to the ones place. Here we know up to the 10,000ths place. 1 is least precise, so we're going to underline up to the ones place. Ask if the number next to it is a 5 or greater. It is, so we'll round up here. We get an answer of 58. Let's do another example. In this case, the addition is in parentheses, so that's what we're going to focus on first. I like to always add this way, so I'm going to put it up here so we can see it. 13.1 plus 0.076 would give us an answer of 13.176. But when we add, we're looking again at precision. This we knew up to the tenths place. This we knew up to the thousandths place. So therefore our answer, we would only know up to the tenths place. But do we get rid of these numbers over here? No, you're going to keep them and use them for the next part of the calculation, but you're going to keep in mind that you only knew up to the tenths place there. So now we've got 13.176, knowing up to the tenths place, times 14.462. 13.176 times 14462 gives me 190,000. 551.31. All right, so this one we knew up to the tenths place, which told us that we knew those 3 sig figs. And that's important because now we multiplied or divided. Now we're looking at sig figs, right? So remember, anytime we add or subtract, we're looking at precision. Anytime we multiply or divide, we're going to be looking at sig figs. But we don't just know all those 5 numbers, we know only the 3 that we underlined that we determined from the first step up here. So now we've got 3 sig figs times something with 5 sig figs is going to give us an answer with something with 3 sig figs. So this one needs to have 3. Now remember, when you multiply and divide, it's easier to put it in scientific notation first before you round. So let's go ahead and do that. We're going to move the decimal 1, 2, 3, 4, 5 times. So we got 1.9055131 times 10 to the 5. And again, it's gotta have 3 sig figs. So I underline the first 3. I skip the numbers 5 or greater. If this had been exactly 5, we would have done our even odd, but it's not exactly 5. It's 5, 5, 1, 3, 1. So it's bigger than a 5. And so our answer, this is bigger than a 5, so we're gonna round up, is 1.91 times 10 to the 5th, also known as 191,000. And both of those answers would be correct. All right, now we're gonna move on to a different section, and this is gonna set you up a lot better for worksheet number 2. And that's understanding how units work. So a little bit ago, I told you densities in units of grams per milliliter or grams per centimeter cubed, right? Not knowing anything about the calculation, if grams per centimeter cubed or grams per milliliter was in your answer, so for example, if you had a multiple choice, it was A, B, C, and you didn't know anything about the calculation, but the units were grams per milliliter in each of these, you would have known how to do the problem, because you would know that you need to take the stuff with the grams and divide it by the stuff with the milliliters, and you would have gotten your answer. And that's something, for some reason, it took me a long time in college to figure out. So that's why I go over how important units are and understanding. So let's go ahead and look at these. We have grams times grams over milliliters times, or millimeters times millimeters. And what you're gonna get, grams times grams, anytime you like take 2 times 2, that would be like 2 squared, right? Or 2 times 2 times 2 would be 2 cubed. The same with units. So here on our top, on our numerator, we got grams times grams. That would be grams squared. And then our denominator, we got millimeters times millimeters, which would be millimeters squared. Cool. Over here, we've got grams over centimeters times centimeters times centimeters, which would be centimeters cubed. Over here, we have square root of centimeters times centimeters, which would be the square root of centimeters squared over liters. And if you take the square root of something squared, in other words, if I were to take the square root of this over here, this 2 squared, I'd get 2 back. It's the same reason you would get centimeters over liters here. Last but not least, no idea what I was doing here, but let's go ahead and figure it out. So we've got joules times liters divided by mole K, all divided by liters times mole squared. What's that? You can't see it. Okay, so if I have something over here and I'm dividing it by something right here, I kind of want to go over it real quick to show you mathematically how you do that. So for example, if you have 1/2 and you divide it by 2, if you have a half of something and you divide it by 2, you get a 1/4, right? In other words, you can see that number goes over here and multiplies. That equals 1/4. And the same thing over here. This number right here will come up here. And so now we've got joules times liters over mole K times liters times mole squared. Mole squared times mole would be mole cubed, and the liters are going to cancel. So I get joules over mole cubed times K. Don't know what I was thinking, but that was really fun. Alrighty. Now we're moving on to the last part, which says, what are the answers, including units, to the following calculations? So now we're working with measurements that actually have units written. And That's going to be, that's when we know for sure that sig figs are going to be important. So 47.2 times 1.0 would give us 47.2, but we know about sig figs now, right? We know that this has 3 and this has 2, so it's not 47.2, and now the answer is actually 47. And then we take our units. We had centimeters times centimeters. In other words, centimeters squared. I wrote cubed. And that would be our answer. Our next question, we have 14.1 plus 2.017. So 14.1 plus 2.07. 2, 7, a 1, a 6, and a 1, and decimal 16.17. This is inches, and this is inches. So we're going to be looking at precision. This one we know to the tenths. This one we know to the hundredths. Therefore, this answer we know to the tenths. We underline it, we ask if the number next to it's 5 or greater. It is, so we're going to round up. We get 16.2. And then whenever you add units, in fact, you can only add things that are either unitless with a unit or that are the same unit. This would be inch. And this should make sense if we've got if I say, hey, I've got this measurement, this one thing is 14.1, and then we're going to add 2.07. How many inches is there? Your answer would be 16.2. This is, I'm kind of glad I asked this question. It has you set stuff up and say, what are the units of R? If P is in ATM, V is in liter, N is in mole, T is in what's called Kelvin. All right. Well, first we're looking for units of R, so what I'm going to do is I'm going to arrange this equation so that I have R all alone on one side. So I'm just going to divide by N and T on both sides. In other words, PV divided by NT equals R. So if I ask you for the units, well, the units, I'm just going to go ahead and input each unit for each variable. So I'd have ATM times liter. The N is in mole, and the T is in K. And why is this important? Well, you're eventually, just like I showed you those multiple choice answers, A, B, C, D, E, you're going to eventually get a question in gas laws that's like this, where units end up being really important. And they'll have answers that have various ratios of this, your various units. And you're going to be able to figure out what you need to do based solely on this. If you have the pressure and you multiply it by the volume, if you have the pressure in ATM, you multiply the volume in liters and you divide it by the moles times the Kelvin, you're going to get your answer. And that's the beautiful part about it. Okay, circle the exact numbers. So there are some cases where we're not looking at sig figs. So exact numbers have infinite number of sig figs. What do I mean by that? Well, until now we've been talking about measurements, right? Things that have a range. So if I were to say, hey, I measured this thing, it's 64 feet long, you know that this has 2 sig figs, and it's a range between 63 and 65. But if I say, hey, there are 60 seconds in a minute, and I'm like, yeah, that means there's between 50 and 70 seconds in a minute, you'd look at me funny. That's because this conversion right here is exact. It's not 60 seconds per, it's not a range here, it's not something with 1 sig fig. It is exactly 60.0000000000 on and on and on seconds per minute, because this is the definition of a minute. Same thing with hours, minutes to hours, 60 minutes per hour. And this has, see all those zeros that come after the number with a decimal somewhere in that number? this would have infinite number of sig figs. And those are exact numbers. If you went and you ate some grapes, I don't know why I'm drawing grapes. I am not an artist. I should never draw anything. Okay, so these are your grapes. If you went and ate 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you went and ate all 10 of these grapes, and you knew exactly how many you ate, you didn't eat somewhere between 9 and 11. You ate exactly 10. So when things are not measurements, when it's not a measurement, it's exact. So when you're not using a number to measure something, it's going to be an exact number. So let's talk about the first question here. We had 14 feet. 14 feet, that's not, you're not counting something, you're not giving a conversion. 14 feet is a measurement. So this has 2 sig figs. 12 inches and a foot. This, you're not measuring something with 12 inches per foot. This is a conversion. In fact, let me write these out. This one is a measurement. And anytime it's not a measurement, it's exact. This is exact. It's got 12.00000 on and on inches per foot. 65 apples. Apples, last I checked, is not a unit of measurement. This is counting something. So whenever you count something, just like the grapes, it's exact. 65 apples would be 65.00000 apples. 65 seconds. We measure time. And because we measure time, this is a measurement. 60 seconds per minute. We already used that example up here. You know that this is a conversion. And it is exact. There are exactly 60 seconds per minute. And last but not least, 1,000 millimeters. 1,000 millimeters. Millimeters is a measurement. And therefore, this would only have 1 sig fig. So this guy has 2 sig figs, this guy has 2 sig figs, this one has 1 sig fig. And anything circled has an infinite number of sig figs, which we will use in the next lesson. All right, y'all, have a great week. I'll see you Thursday.